So again, my name is Brad Miro. I'm a developer program engineer at Google, and my role consists about 50-50 of working on traditional software engineering as well as going to conferences and speaking and talking to developers and learning about some of the things that you're working on and how we can help you in our tools. And so I specifically work in the machine learning and big data spaces, so I do a lot of work with Spark, and I do a lot of work with TensorFlow, which I'm going to talk to you about today. Specifically, we'll discuss TensorFlow 2.0 and how you can get started with it and use it for deep learning. So before we dive in, I always like to ask the group, this is an AI conference, of course, but I just want to ask, who here has actually built anything in machine learning or project in production? Just a quick show of hands. Okay, awesome. And what about deep learning specifically? Cool. And who here has used TensorFlow before? Any version, 1.x, 2.0? Anyone use 2.0? Cool. Okay, that's great. I just like to do that to see, just get a feel for it and whatnot. Thank you. So today we're going to talk about TensorFlow 2.0. We're going to start with just an introduction to deep learning and what it is. We'll then discuss TensorFlow, and I'll introduce it to you generally. We'll then discuss how TensorFlow is being used at Google. Followed up with TensorFlow 2.0, and I'll go through some examples and some of the new features that are available with it. And then last but not least, I'll explain to you how you can get started actually building deep learning models with TensorFlow 2.0. So we'll just dive right in. I'll start off with deep learning. And I just want to do a quick shout out to my colleague, Dale Markowitz. You're going to see some lovely doodles in some of the upcoming slides, and they were all designed by her. She's actually giving a talk here later today at 4:10 on AutoML, so I definitely recommend you sticking around and checking it out. It should be really awesome. So deep learning. So for those of you who have worked with traditional machine learning before, you know that you'll take a set of data and then you'll train a model on it that will help you effectively predict what new data that comes in that might be classified as. So for instance, let's say we have a data set that represents, let's say, the height, the width, and the weight of a set of animals. So let's say these are all labeled as either cats or dogs. So what you can do is you can then take all this data, you can graph it, you can see what the relationships are, and you might start to see that there's a bit of a divide in where the data actually sits. And so with that, you can then create what we call like a line of best fit or something like a boundary that can actually divide the two, so that when you have a new set of data that you don't necessarily know right away if it's a cat or a dog, the algorithm can help you predict what it might be. And so you might do that with something like linear regression, a traditional statistical machine learning method. So in this case, we'll start with some set of random weights. You'll see how accurate the line is on some set of test data, and you'll iterate over it, and then eventually the line will converge on what it feels is the most accurate representation of your data for future predictions. Well, let's say you start to work with some more complex data. So in this case, before we were using just quantitative data, just numbers like a small amount. But let's say we start to work with something like photos. So instead of a height, width, and weight of the cats and dogs, let's say we then have images of cats and dogs. How can we actually work with these to be able to build a model that works really well? And so if you imagine how a computer views an image, so it's made up of a bunch of pixels, and especially if it's a color image, each one of these pixels will have a red, green, and blue value, somewhere between 0 to 255. And then what that'll end up being is that you can then take the image and represent it as a 3D tensor, where each pixel value represents the red, green, and blue values given to work in the tensor itself. And so once we have this data, we can then actually take it and create a more complex model with it. And so we can build something that's called a neural network. So neural networks are effectively just another type of machine learning, but they represent the field of what we call deep learning fundamentals. And these neural networks are the foundational algorithms that allow us to create deep neural networks. And so how do these things work? So there's actually several different types of neural networks, but just to generalize, the idea here is that you take all of the data that you have, you perform some function on it. So in the example we have here, you can take the data, you could then add it together, and then you apply something what we call an activation function on the data. And what that will do is it will just remove the linearity in the data so that it actually becomes representative. So a really common example is something called the relative function, the REL function. And what that will do is that will take all of the data that you have, and it will take any negative value, it says it's 0, and just do positive ones that one. And what that will do is it will remove the linearities from the data and make it to actually form the basis of a model. So So what you can then do is when you have these neurons, you can actually link them together and begin to form what we call neural networks. So in this example here, we have pictures of cats, we have pictures of dogs, and then we're actually beginning to train a neuron. So you can see here that there's these multiple different layers that are interconnected, and these each represent a separate set of neurons. And you might be thinking, well, this sounds kind of similar to how neurons in our brain might work. And that's effectively where this loosely comes from. It's based on our brains and the neural networks and the connections and synapses that we all have. And so you can start to build these models, you can then feed in these images, and then the model will start to become representative. We'll start to learn what a cat looks like, what a dog looks like. So for images like these, it becomes pretty easy because this is obviously a cat, this is obviously a dog. But then if you have an image like this that might not necessarily be as clear just from the get-go, this is where these models really start to shine, and then you can take a look at this and see what this image might actually be. And so the reason that we call these deep neural networks is because they effectively represent they're multiple layers. So fundamentally, all you need for a neural network is to just have an input layer, a hidden layer, which is just a layer in the middle, and an output layer. But what we can actually do is we can tack on multiple of these hidden layers, 2 hidden layers, we get up to 20 hidden layers. That just end up becoming, it creates a more powerful model, and that's where deep code comes from. You start tacking on more of these. And so what these are fundamentally doing in terms of image recognition. So in this case, let's say we have a 3-layer neuron. So we start with an image of this dog. And then the earlier layers will basically figure out lower level features. So the first layer will just be looking for edges. It'll be looking for straight lines. It'll be looking for curves. Very basic shapes. I can draw them out like a movie. But as we go deeper into the neural network, the features that we end up finding become more and more complex. So in this case, the first layer might be straight lines. The next layer might be slightly more complex shapes. You might start to see squares. You might start to see things that may be loosely representative of what you might see now around it up. But then as you get towards the end of the neural network, you start to see more complex features being located. And so you'll start to see faces of the animals. You'll start to see paws. You'll start to see tails and things like that. So that's effectively how it works. And then in this case, the output would then be, in this model, since we're looking for just cats or dogs, the output will be one or the other with some degree of confidence. So like in this case, this is saying it's 99% chance that it's a dog. It could be less, it could be more, it could be 99%. But that's effectively what these things are doing. So when you should actually use deep learning, I think there's a lot of discussion around this nowadays that I'm seeing. And I think it's very common to, what I like to say, deep learning all of the things. And just given any machine learning model, or any project that you have that you want to use machine learning, you just automatically throw deep learning at it. I do not recommend that approach. I think there are some loosely defined but fairly good rule of thumbs to follow for actually using deep learning in your projects. And so one of the first things I recommend, and there's a huge asterisk on this one that we'll touch on later, but the idea is if you want to build a neural network from scratch, you should really only do it if you have around, let's say, 10,000 plus examples. It's usually a good place to start. These things are really data hungry, but they are great when you do have a lot of data, because a lot of traditional models will tend to plateau once you keep throwing data at it, and there's only you can only make the models so accurate or so effective for your use case. The deep learning does tend to scale really well as you keep throwing data at it, and it does continue to get better and better. But some other traditional models may not be as good at it. The problem is complex. And what I mean by this is that if you're working with data that, if you were to just take a look at it visually, like, so if you were to take data and if you were to look at the way the computer sees it, for instance, something like an image, the computer's not actually seeing an image, you're seeing an image. But the computer's seeing the red, green, and blue values. Now, if you're a human and you're just looking at the values themselves, those aren't going to make very much sense to you. But it will to a computer, and this is where we say that the data starts to become complex and the problem becomes complex. So good examples of this are speech, vision, because the spectrograms are, of course, fairly meaningless to the data of the spectrogram are fairly meaningless to you, and natural language, just because tagging necessary text can just be really difficult to work with. So we also consider that complex problem. Something that these all have in common is that the data is unstructured in all of them. So again, if you're working with unstructured data, deep learning is a really good tool to use because by nature it starts to develop, it starts to build those relationships for you with the data that you would otherwise be doing using traditional feature. And then also, you need the absolute best of models, I think is another good use case. So deep learning models do tend to be really accurate, but they do tend to be really computationally expensive and they can take a while to train. And for a lot of use cases out there, you don't absolutely need to get, go from 99.9% to 0.99%. Like you just don't need to, and it's just not necessary for you to do so. And that's of course on a case-by-case basis. That's up to you to figure out if that's appropriate for your use case. So that being said, these are some cases where you can use deep learning, but I don't recommend using deep learning if you don't have a large data set. Again, like these things do tend to be really data hungry if you're building one from scratch. If you're also performing sufficiently well with traditional machine learning methods, something like linear regression is actually a really great tool and can honestly get you most of the way for a lot of different use cases. So unless you know for sure that you really want to use deep learning, like if you're working with computer vision, I really recommend trying linear regression. Try random forests. Try some of the more traditional ones and just see how they perform. They might be good enough for your use case. Your data is structured, and you possess the proper domain knowledge. So again, this goes back to what we were saying before. Deep learning is unstructured data because it can build those relationships underneath of it. But sometimes if your data is already structured and there's some meaning to it, for instance, if one of the canonical examples for learning about linear regression is to predict housing prices, that data is pretty well defined. The data is usually the size of the house, the location of the house, how much the house costs, and things like that. So in that case, deep learning might just be overkill. They might be able to get away with some of the other traditional methods. And then also your model, if your model needs to be explainable. This is one of the biggest problems with deep learning today, is that if you actually need to figure out how the model made its prediction, it can sometimes be difficult to do. So again, that's dependent on your use case, but if explainability is something that's really important to you, definitely look into this and maybe use something like random forests, which tend to be a bit better at explaining how the model came to be. Okay, so that was deep learning, and now I would like to introduce TensorFlow. So what is TensorFlow? It is an open source deep learning library that Google released in 2015. We were actually using it internally for a few years before then, but we decided to release it to the world and let everyone else, get on the fun in 2015. And so it contains utilities to help you write neural networks. A lot of building this stuff and having it operate with the hardware and mathematical computations actually does require a lot of very specific domain knowledge that in some cases is really exciting, but in a lot of cases it can just it's a lot of repeat work that you don't necessarily want to build from scratch. So you can leverage the tools that TensorFlow contains so that you don't have to build these things from scratch yourself. TensorFlow is perfectly suited to work with GPUs and TPUs, these being hardware accelerators that are really good at working with the computations that deep learning models typically tend to need. To date, we have over 2,000 contributors on GitHub, which is super exciting to see the growth of this project. And the beta was actually just released in June last month, so you can check it out. So, as I mentioned, TensorFlow came out in 2015, and we've just seen a tremendous amount of growth in the project over the years. We've continued to add different features to it. TensorBoard has come along since then. Keras, different integrations with other tools, both on the Google Cloud platform and otherwise. TensorFlow.js, just lots of really exciting things, and a bunch of things to touch on throughout the duration of the talk. Using TensorFlow all over the world, I love looking at this map and just seeing how popular the framework is and how it's being, people are able to leverage it to help them with their machine learning and related needs. And then again, just a lot of popularity, all sorts of numbers here, statistics. Awesome. So we use TensorFlow at Google. We developed it. We work very closely with the open source community, but it's the tool that we use internally as well. Now, resolve the AI that we do, so I just want to give you some examples of how I actually use this. So, we are Google. We have data centers all over the place, lots of computation, using up a lot of resources. And what we're actually able to do is we're able to use AI and TensorFlow to help us make these data centers more efficient so that we're not using as much power, so that we're providing faster results to our users. And we're really able to just leverage these sorts of technologies to make this stuff as good as it possibly can be. We also use this for global localization in Google Maps. So some of you may have used this feature before, but it's actually really awesome if you're navigating a city, especially one like New York City, for those of you who live downtown. It's really awesome. It helps you figure out where you should go by just displaying the map directly on your screen. So you're walking, let's say go to the left, and hopefully go to the left. And so we're using machine learning and TensorFlow to help power that, as well as the portrait mode on the Google Pixel. So what we're able to do is we can actually use AI and sorts of things to help blur out the background on an image so that you can have the focal point of the image really stand out in the picture. And then so a little bit more on the research side of things. So in this case, we're actually able to generate music. So this is effectively a synthesizer where you can drag the dot over the pad and it will generate music. And this is done using AI, using a technique called different kinds of generative methods. We're using TensorFlow for lots of exciting medical research projects. So in this case, we're working on a project called Predict something called diabetic retinopathy. So on the left, you'll see a picture of what we might consider a healthy eye. And then on the right, we have one that might be considered an unhealthy eye. And so what we can actually do is use AI and TensorFlow to help us predict which one of these is which helps doctors, of course. And then this one's my personal favorite. So I'm a bit of an astronomy buff as well. And so here we're actually able to use this stuff to help us predict if distant objects are planets. And so just a very brief astronomy lesson. So if you imagine that you have a really bright object in the sky, let's say the sun. And from here, if let's say Mercury passes in front of the sun, the brightness of the sun is going to decrease ever so slightly from our point of view, because there's technically an object between us. And so what we can actually do is we can predict, or we can detect the brightness fluctuations from our point of view, and then predict whether or not these types of objects represent planets. But we can do that with planets that are light years, many, many light years away. And so we've been using TensorFlow machine learning to help us predict if these objects are in fact distant planets. That makes pretty cool. Can everyone hear me all right, by the way? I realize I don't have a microphone. I should invest in everything. Okay, cool. Great. So now let's talk about 2.0 and what are some of the new features we can play around with. So for those of you who have used 1.x before, I'll be completely empathetic here. There are definitely a lot of things about it that were frustrating or not entirely easy to use. There's a lot of different ways to do more or less the same thing. There are just many things about it. Session.run, it's kind of in the butt to me sometimes. So we've taken a lot of the feedback, both from internal usage and also from the community, and implemented these things to make TensorFlow just as great and as easy of an experience as we possibly can. And so one of the first things we did was we simplified the PIs. We took out a lot of the stuff that's just not fun to use, just not necessary to use, and we've either gotten rid of it or we've just consolidated it to have more of the, let's say, 1 or 2 good ways to do a certain thing instead of 5 or 6. We've also focused on using Keras as our high-level API, and for those of you who have used Keras before, it's personally my favorite framework to use. I think it's a lot of fun, and so I hope you all agree. We're going to talk a little bit more about that in just a moment, but we're focusing on Keras with TensorFlow. And then we've also taken eager execution and made it the default mode of using TensorFlow. And so what that effectively means, for those of you who have used TensorFlow 1.x, we have using session.run, you have to build the model and then run it. But now you can just run it like normal Python. We want TensorFlow to be powerful. We want it to be flexible. We want it to be scalable. So for that, TensorFlow 2.0 is perfectly suited for research, for production on as many as hundreds of machines to as little as your laptop, depending on the use case, of course. And we want it to be able to deploy everywhere. We want this to be super flexible. And with that, we have different methods and different places, frameworks for you to actually be able to do this. So if you want to deploy your models on servers, you can use TensorFlow Extended, which is, and all of this is open source, by the way. TensorFlow Extended is an open source package for running your models, or deploying your models on servers. TensorFlow Lite is a package for deploying your models on edge devices, Android phones, iOS, Raspberry Pis, all sorts of fun tools. And then if you want to deploy it in the browser, you can actually use TensorFlow.js, which is another really exciting project that we're working on. But how does this work? How is it that we're able to take any model and just deploy it on any of this? So the way we use something called the saved model format. And so the way that effectively works is, if you look at the top left here, if you're training a model, you'll read read and process data. You'll then actually train the model using something like Keras or premium estimators. You'll then train this, you'll distribute it via on the cores of your your laptop, a GPU cluster, CPU cluster, what have you. But then you can export the model to the saved model format, then load it up into any one of the deployment methods that we talked about before. So TensorFlow serving, which is part of TensorFlow extended, TensorFlow Lite, TensorFlow.js. But then also we have other language bindings, languages such as C, Java, and Go. And this is all using the same model. So for instance, let's say you were building, if you wanted to build a phone app, one way that you could potentially do it is to use something like Python, train a model, put it on a GPU cluster, export it, and then run it on your phone using TensorFlow. Let you once again use these. We also have different libraries available that are built on top of TensorFlow for more niche use cases. So for instance, we have a package called TF Agents, which has a lot of tools to deal with reinforcement learning. We have TF Text for natural language processing. And these are all built on top of TensorFlow, all open source, and are really exciting. There's a whole list of these depending on what your specific use cases. You can use TensorFlow 2.0 like NumPy. So earlier I was discussing eager execution, and that's effectively what we were going for to make the experience as seamless as possible, using something like NumPy going through TensorFlow. And the idea here is that this code works. This didn't work in 1.x. You go to initialize the variables, you then to run it. It's just a lot of things you need to do, and now you don't need to. It'll just run directly like NumPy. If you want to code it, you can actually have computations be happening. So with that, let's just discuss some specifics of what's gone and what's new. So to start from what's gone, session.run, I've mentioned it a couple of times, gone. No longer need to do it. Your code runs just like regular Python. The usage of control dependencies and your conditionals or while loops, those are all gone. You now just use regular Python reservoirs, so you can use the while, you can use Python while, Python if. That's all available to use now. Global variables initializer, you don't have to do that. You just initialize by default. And then TF.contrib was actually moved out of the main release of TensorFlow for good reason. It got so large that it just wasn't realistic to include it with every installation of TensorFlow. It's great, and it exists in a separate repository, and we're so happy that this is a problem that we're having. But this is what we definitely had to do. That being said, we have some new things. So eager execution by default. It was around in 1.x, but we have now enabled it by default in 2.0, which is super exciting. We have tf.function, which is a wrapper that lets you take any Python code and compile it into TensorFlow code, which is why you can now get away with using your Python while statements, your Python if statements, things of that nature. And then we've introduced Keras as the main high-level API. So let's just dive into that a little bit more. So tf.keras. We love Keras. Keras is great. It's a lot of fun. Fairly easy to use in comparison to some other tools out there. So what we've done is we've just made it a part of the core TensorFlow release. If you can install TensorFlow, we have tf.keras available with it. How this stands in comparison to regular Keras, they are technically separate projects. You do not need to install Keras normally to use tf.keras. They are separate. They are otherwise exactly the same. The creator, Keras, Francois Chalet, actually works, he's an engineer Google, so he's helping out a lot, making the two libraries very similar and making the experience as seamless as possible. But if you do import Keras or from TensorFlow import Keras on the same code, it should work. The reason behind this, so Keras in and of itself is actually an API spec. It's not a computing engine of any sort. So Keras, by nature, needs something behind it. And so that's traditionally been either Piano or TensorFlow. So now with tf.keras, it's just TensorFlow by default when you want to configure it. So when you're using Keras with TensorFlow, there's two ways that I like to describe how you can use it. One I say is for beginners, one I say is for experts. Those are very loose definitions, and I honestly like the beginner method better. I think it's a bit easy to use. But I'll go over both of them, and feel free to use whichever one is more appropriate for your use case. So the first one is the beginner's method. And the idea here is when you're building a deep neural network, each layer of the network ends up just being effectively a single line of code. This would otherwise require a lot of math and computations that could become tedious doing again and again. But we have these layers built in. You can just import them and add them to a model object and then effectively a model. So once you build this, You then compile it and you provide the optimizer, the loss function, and the metrics that you're looking for. You can then fit it on your training data and evaluate it on your test data. It's pretty straightforward, pretty easy. This is the whole working model. So then we have what we call experts. And so this is just using Python subclassing. This gives you a bit more control and it lets you do some other things that might be a little bit more difficult to do with the sequential object. So you just create a model subclass and then you add a call function. And you can treat this object like any other comparison. So what's the difference between these two fundamentally? So the first method is the symbolic method for beginners. The model compiles to a graph of layers underneath the hood. Any graph that you compile will run, and then TensorFlow does a lot of the work in helping you debug and make sure that the model is sensible, and that the errors will be caught compiled times that you don't run into these later on. Now, how does this compare to the for experts method, or what we call the imperative method? Your model is Python bytecode because you're just creating a Python class. You have complete flexibility and control over what you're doing, but by nature, it is obviously going to be harder to debug and then harder to maintain. But they're both great, and they both have their applicable use cases. Okay, so next up we'll talk about tf.function. So I mentioned this a bit earlier, but this is effectively the magic behind being able to use regular Python code and compile it in TensorFlow. So let's say we have this function here. In this case, we're just creating what we call an LSTM cell. This is just a type of neural layer in a neural network. You don't have to be concerned about it. But it's effectively just a function that creates an object. So if we wanted to just speed this up, all we have to do is add this wrapper. Just tf.function and undo it, and then it will automatically speed up what it is that you're trying to do. And so the way that this actually works is if we have this other function here, let's say, so this is just going to reduce a bunch of numbers, sum up a bunch of numbers, and then do the hyperbolic tangent function on top of them. What this will do is it will take this code line function and then convert it to this code that you see here. And you can actually take a look at this by running the tf.autograph.code function. This is strictly for educational use. You don't have to do this for your code to run. But it can sometimes be kind of cool to see what TensorFlow is actually doing to make the code work. So it's a little bit of a mess, but it's kind of interesting. Okay, so next up we'll talk about distribution strategies. And so what we want to do is we mentioned that TensorFlow is flexible and scalable, and we want you to be able to do that fairly seamlessly, fairly easily. So how can you do that? If you have this code here, this is another example of the basic terrace model. Let's say you've trained this on your laptop or on a small cluster and you've used just a little bit of data, and you want to scale this. All you have to do is include this within the scope of one of your distribution strategies. So in this case, we're referencing the Miro strategy, which will more or less take the model that you have and distribute it over each GPU equally. There's other examples where you might take your model and split the model up itself. It's a little bit outside of the scope of this talk, but the idea is depending on what it is that you're looking to do, you have options available to you just by adding a couple lines of code to the top of the model that you're working on. Okay, TensorFlow datasets. This is personally one of my favorite features that's coming with it, that's available in TensorFlow. So this actually is a separate library, but what this is it contains a whole set of data sets that are readily available for you to use that you can load in and then split up between your training and your test data sets and just get to work. In this case, I'm referencing the cats versus dogs data set, but there's plenty of examples. All of them are available at TensorFlow.org/datasets. But here you can see we have MNIST, we have Titanic, IMDb reviews, CFAR10, a bunch of these probably familiar, ImageNet. So there's a whole bunch of these, take a look, all available for you to use. And so what you can actually do is you can take this and apply it with a technique called transfer learning that we're going to talk about. And this will let you effectively build a model from scratch using tools that are already readily available. So transfer learning, if we go back to the example that we had earlier, just to give an introduction on the transfer learning case. So we were mentioning how earlier this model, the earlier features that are detected, straight lines and circles and shapes, no matter what image that you're trying to predict, that's going to look the same no matter what. A straight line is always going to be a straight line. A square is always going to be a square. And so in the past several years, what our researchers have been able to realize is that we can actually reuse the trainings that we've done on previous models and reuse them in new ones. So what we can effectively do is we can cut out this beginner section, that are detecting the lower level features, and reuse these for other models. And where this really comes into play is, let's say you only have, if you're doing image recognition, but you only have, let's say, 200 images of something that you're trying to detect, you can leverage these other pre-trained models with using transfer learning and actually build something that works super well. And so TensorFlow in and of itself actually has some of these built into it already. So in this case, we're referencing MobileNet version 2, trained on ImageNet. So you can use this, you can set that, you can say don't train this specific piece of the model, and then you can just tack on an output layer at the end of that, and then you build up, you have an entire model that's 80% of the way already trained. Now, in addition to this, we also have TensorFlow Hub. And so TensorFlow Hub is it's a website that contains all sorts of different models that you can leverage with transfer learning. So definitely take a look there. These are all free and totally open source, so I definitely recommend you taking a look at these. And what I think is really neat is between leveraging one of these and leveraging one of the TensorFlow data sets, you have an entire model. You have the tools to build an entire model as long as you just add a couple of things to that, which I think is really cool. Okay, so we just got an overview of some of the tools available in TensorFlow 2.0. What if you want to upgrade? What if you're already using 1.x? You want to upgrade to 2.0. How can you do that? So we have a ton of migration guides available for you at tensorflow.org just tensorflow.org. You can check out migration guides there. We also have a library called tf.path.v1 that will give you access to any of the APIs that weren't necessarily translated over to TensorFlow 2.0 yet. You can just reference them here. Then we also have an upgrade script, TF upgrade script. So the way that this works, for anyone who's ever used the Python 2 to 3 script to convert the Python 2 script to Python 3, it's effectively the same thing. You just plug in your input file and an output file, and it'll actually create a new file that did all the mappings for you between 1.x and 2.0, and then tell you what changed. In some cases, the APIs are the same. In others, you have the name change. In others, it was deprecated, and so it'll be referencing the TF.path.v1. What if you're just interested in getting started? You don't need to upgrade, or you just want to learn about TensorFlow 2.0 again. We have lots of resources available to you. The first thing I should recommend you doing is installing it. You can get this just via simple pip install. As of today, the beta is currently available. So definitely go do that at the conclusion of this talk, or right now. I won't stop you. Please, go ahead. You can also learn more about this at tensorflow.org. We have code labs, we have tutorials doing all sorts of different things for all sorts of use cases. So I highly recommend you start here. Some of the resources we have available. We have courses available. We have partnerships with deeplearning.ai, Coursera, and Udacity. All of them contain TensorFlow courses utilizing 2.0. Definitely recommend you checking out those as well. Super well done. All done with other members of the TensorFlow team. And then, lastly, I just want to talk about two other really exciting projects that are happening within the TensorFlow community. The first one is Swift for TensorFlow. So for those of you who have used Swift before, it's actually a really fun language to use, and it does shore up a lot of the, for lack of a better word, problems that others have seen with Python, and that it can sometimes be a bit faster in certain use cases. But there's a lot of work being done here, so if you're interested more in this project, I definitely highly recommend it. And then TensorFlow.js, which I mentioned earlier in the presentation. Be able to actually train models in TensorFlow as well as deploy them using TensorFlow.js. Super exciting, so if these are projects that interest you, definitely highly recommend you explore and continue to learn about these as well. And then if you're interested in getting involved in the project, we're on GitHub. We'd love to have community. We'd love to hear your feedback. We'd love for your support. If you have any features or any suggestions or anything you'd like to see or want to build yourself, again, this is totally open source, so we'd love to have you come along for the ride. And with that, I issue a call to action to go build, so you can download TensorFlow here, simple pip install. And thanks for coming.
but then it's hard to rewrite. So what do you mean by more flexible? We can do the same thing with TensorFlow with we can control the layers and
Sure. So the question was just a little bit more about the difference between the beginner's method for TensorFlow.keras and the expert's method for TensorFlow.keras. So the idea is, if you're using the beginner's method, each layer is already built for you. So these things, like each layer would generally involve a lot of like mathematics to be able to build a thing from scratch. But they otherwise, like you can generalize what a layer should look like for most of these cases. So if you don't need to have a custom one, like generally for the expert's method is more along the lines of like research. When you're like building something and you need to try a specific thing, you know, maybe you want to tweak this type of layer and it's just not something that's readily available because it's something new that you're working on. You'll have more flexibility to build something like that with the expert's method because you're actually building the layers from scratch as opposed to using ones that already exist. So I'd say that's one of the main advantages to maybe using the expert's method. But it really, for most use cases, like what you're working with the beginner's method, it should be more than enough.
So you said that once you build the TensorFlow model, you get a graph. So it's basically a graph. So I'm sure that I use the TensorFlow inspector to visualize the graph, right?
Sure.
I mean, using TensorFlow also you can visualize the graph. So my point is, so suppose let's say I see the graph, I see unnecessary nodes over there. I need to prune. Can I able to prune the graph once I build it, or I need to go back and recode and then I have to build the graph again?
Okay. So the question was, if you've already built a TensorFlow model and you have extra nodes that you don't necessarily need, is there a way to prune it? So off the top of my head, like the best way I would do it would be to redo it. I guess it would sort of depend on what it is that you're actually doing. If you built the model and that those extra pieces rely on, like the other parts of the model are a function of that piece, then you'll have to redo it. I guess it sort of depends on like what it is that you're doing. But off the top of my head, I can't necessarily think of what to do. So there definitely might be. Sure.
Coming back to the first question, the other difference I understand is, for instance, that in the basic version you cannot have multiple outputs, right? Versus in the other one they have multiple outputs.
Sure. So the question/observation that you gave was that for the beginner's keras method, you couldn't necessarily have multiple outputs, but the expert's method you can. So that's definitely one way that you could definitely utilize that. And just give you complete flexibility in whatever it is that you're trying to do. The expert's method is definitely well suited to your point.
And my question is, what about the differences between 1.x and 2 on the tensor server? Are there any?
Sure. So the question is TensorFlow serving the differences between 1.x and 2.0. From a high level, I can't necessarily think of anything off the top of my head. I mean, they're fundamentally doing the same thing, but there might be some things underneath the hood. I'm not entirely sure. But they're all available if you're interested in further into it. Let's take one over here.
Can you tell me a little more about the privacy library?
Sure.
What is it? What is good for best practice?
Sure. So the question was regarding regards to TensorFlow privacy. So this is another package that sits on top of TensorFlow. So that's really used when you're working with data that is really sensitive. And so when you're working with, for instance, like PII, personal information, like for information that pertains to people, the email addresses, names, social security numbers. What this will effectively do is, underneath the hood, it will take it and make it, it'll hash it or do things with it so that it doesn't become as accessible. And if someone else were to try and make, like if you were to maybe give the model to someone else, like it'd be very difficult for them to reverse engineer the model to see the things that it was that it's trained on. So that's, I mean, really in any instance where the data that you're working with is sensitive, that's where you're definitely best suited.
How about access to low-level information like direct access to gradients, right, which you do have today, right, in TensorFlow? Is that still available there?
Yeah, so the question was, and forgive me if I misheard you, the question was if you still have access to gradients, like something like the gradient tape.
Yeah, compute gradients, for example, right, function.
Yeah, so you still have access to all of that, and with that you're then able to create those custom models and things of that nature. You have access to all of the same stuff that you did.
Could you speak to the, I guess, between 1.0 and 2.0? Because like, it's just the vast experience using Keras as the top layer on top of TensorFlow or a different library, there's the performance impact that can't do some of the optimization and do it running with your code all the time.
Sure. So the question was some of the performance differences between TensorFlow 1.x and TensorFlow 2.0, also as they pertain to Keras. So I don't have specific numbers off the top of my head, but the idea is that because we've integrated Keras within TensorFlow specifically on the TensorFlow engine, a lot of those potential issues and conversions are taken care of on the back end. So naturally, we see some improvements. I do apologize I don't have numbers, but I'm happy to take a look at those and get back to you. Yeah.
So, what do you thought about like TensorFlow versus Python? Right, there's a Python out there, so I want to know what's your advantage that if I'm using TensorFlow versus that, and something like that. You know.
Can you repeat that? I'm sorry.
I say that's like what is the difference between TensorFlow versus Python? Python?
Oh,
PyTorch.
PyTorch. Okay.
Yeah.
Yes.
So what is you recommended for beginner to study? Because I heard a lot of TensorFlow is really great because it's supported by Google, but sometimes it's pretty tedious for beginner or something like that. So what is your like if I were using TensorFlow, what's his like advantage versus that?
Sure. So the question was basically the TensorFlow versus PyTorch, especially as it pertains to beginners. I actually love this question because this is obviously kind of what they ask. So I just want to start by saying I love PyTorch. I think it's a super awesome framework. I'm not here to tell you, don't use PyTorch, only use TensorFlow. I think they both definitely have their strengths. As they pertain to beginners, I have personally found Keras to be a little easier to use than some of the PyTorch operators, but the TensorFlow specific operators I have found to sometimes be a little bit more frustrating to use than PyTorch. So I think it might depend a little bit on your use case, but at this point, and I think we'll even continue to see this, the two projects more or less continue to converge. Like they're sort of, TensorFlow sees something that looks awesome that maybe PyTorch is doing and vice versa. So I really don't think, I hate to say it almost doesn't matter which one you use because like it's, you're kind of investing in one project versus the other, but I think the best suggestion I have is just pick one and stick with it. One advantage that I see specifically about TensorFlow right now is that you have the flexibility to deploy it in multiple locations. That's not something that I'm aware of that exists with PyTorch. I could be totally wrong about that. But you have a little bit more flexibility in terms of what you can do, I guess, on the end. But really, pick one and stick with it. You'll be able to do a lot of things. Any other questions? I'll stick around for a few minutes too if anyone wants to come up. Yes?
Just a question about the beginners versus the advanced version, and really talking about declarative versus imperative models. And obviously the other competitor in PyTorch is NX now, which is this mixed paradigm. So it seems like really TF 2.0 is addressing a lot of that distinction. And I guess the main question is just how, because both of those are really sort of different approaches that you may need within some full system to address, both an imperative part and a declarative part. And so I really want to talk about where's the meeting point between those two. What ability do you have to sort of transition from the imperative portion of your model, and the declarative model? You sort of more or less have to split them completely, or is there some level of mixed model possible?
Sure. So the question was, where can you potentially use both the beginners and the experts methods together? So the short answer is you completely can, because they were built alongside each other for that reason. So if you're, I think like one of the most common ways to maybe use the experts method is to build your own custom layers that you can then plug into the sequential API. So you have complete interoperability there. Yeah, definitely no concerns about that. Yes.
Amazon's MXNet price itself very fast. How does TensorFlow compare to that? Are you still behind, or you can close the gap? Where in the roadmap given whether
Sure. So the question was, traditionally, I think you said that MXNet can be faster than TensorFlow in some cases. What is the progress being made there? As far as a head-to-head comparison, I'm not entirely sure. What I do know is that a lot of the optimizations in TensorFlow 2.0 continually, as we continuously we'll just keep doing more and more optimizations going on in a sense. At which point point, if there's certain things that AINYC19 is better at than purpose speed, I don't necessarily know like when we'll cross that threshold or if there are plans to specifically look at that. What I can say is that the project does continue to grow and as these things come up or as there are places where there might be for speed improvements, those will get addressed. Anything else? Cool. And again, I'll stick around for a few minutes, so feel free to